For the past few classes we have been talking about membranes, how to separate dissolved salts, ions, biomolecules using different types of membranes, and we will continue in this class on further on membranes. If you look at the membranes, you have membrane processes like microfiltration, ultrafiltration, nanofiltration, reverse osmosis, dialysis, electrodialysis, and so on. Actually each one has different types of membranes. You have hydrophilic membranes, you have hydrophobic membranes. It is used for separating practically a large number of varied components. We did talk about microfiltration some time back. Let me again recap on that. It resembles like a conventional filtration. Okay, so there are small pores in the membrane material. So the solids which are very small, then the pores will go through and the remaining solids will get filtered out. So it is almost like a normal filtration process. So because there are pores, the pressure required is also much less. You use 1 to 2 bar. It is almost like the normal filtration where we also use 2 or 3 or 5 bar pressure. We do not go very high in pressure. But the disadvantages of microfiltration are just like your normal filtration. There is going to be deposition of solids, frequent fouling of membrane. Fouling, I did mention about fouling last time. Fouling could be bacterial or biological in nature, or it could be because of the polarization, that is concentration polarization effects, and so on actually. So microfiltrations do come across this problem, both the fouling as well as the deposition of solids. So buildup of solids on the membrane, how do you minimize it? We can have a depth filters upstream or a normal conventional filter upstream. So it will capture all bigger particles, and then you go to the microfiltration, and then you resort to further filtration. Another disadvantage of microfiltration, because the pressures are not very high, you are going to get a concentrated slurry. You will not get dry solids after filtration. Ideally you would like to have a dry cake after filtration, because the storage or disposal becomes easy, whereas if it is a slurry it may contain about 10, 15, 20% water. So then it is not very nice idea to store it. Where will you store because of 20% water? So membranes will lead you into slurry system, and you can't apply very high pressures because membrane will mechanically get damaged. So that is the disadvantage of that. So what do? Once you do this type of membrane filtration and you want to get rid of the concentrated slurry, sometimes companies will resort to solar drying. That means they will have open space, and maybe they will have a long plastic surfaces on which the slurry is put in, and water will get dried because of the heating, and the solids which you get, you collect it and use it for either further processing or disposal or landfill or animal feed, whatever you think of. So you need to resort to this type of the solar heating. The equation, this is standard equation for the flux. You have the driving force because of the delta P, that is the pressure, and then if it is a compressible material, if you remember the very early class, where we talked about compressible solids and incompressible solids, we have equation like this, delta P raised to the power S, and S we called it as a compressible exponent. So it is 0 for incompressible. So when you substitute 0 in the incompressible, the delta P raised to the power 0 becomes 1. So compressibility will have no effect on the flux, whereas if the cake is compressible, then you put S as 1, then your driving force gets decreased, because if the cake is compressible, what will happen? If you put too much driving force or too much pressure, cake will get compressed and the flow rate gets decreased. So you need to sort of balance between that. So that is why you will have a term delta P raised to the power S in the denominator. In addition, we have terms like V, that is the total volume which you want to filter, eta is the viscosity, W is the slurry concentration, alpha is the specific cake resistance. So this I hope you remember the Darcy's equation, many classes back we studied, and plus you also have Rm, resistance offered by the membrane itself. Okay. Unlike a filter cloth, membranes may offer resistance to flow because the pore sizes are very small, that is why. Okay. Now if resistance offered by the membrane material is very small, and then you get a very simple equation that will give you the volume that is getting permeated or that will pass through the membrane area given by this formula. So this is again like our old filtration equation. This is the governing equation which determines the permeate flow. Now ultrafiltration, of course the pore sizes are very small, and operating pressure is also very high when compared to your the micro, it is 2 to 10 bar. So this is the separation based on the molecular size. So we can use it for separating high molecular weight products into smaller molecular weight products. So we can use it for separating polymers, proteins, colloids from salts, ionic salts. So here the pore size is much smaller than the microfiltration, much smaller, that is why you are resorting to higher pressure. Okay. So when the pore size is very small, you have to go for higher pressure. Here osmotic pressure is also negligible because higher molecular weight of solutes, that is what we are dealing with actually. Okay. Now in ultrafiltration, the flux is based on the concentration polarization. So there is going to be a concentration of the solute build up on the upstream side. So because of that the flow of the solute is getting disturbed, and if you remember a couple of classes back I talked about the concentration polarization and an equation for the flux, which is given by J, the flux is equal to K logarithm Cg by Cb. Cg is the concentration of the solute in the closer to the upstream of the membrane surface or the gel layer. Cb is your bulk, so Cg will be much higher than Cb because of the build up of solid near the upstream surface of the membrane, understand. So K is your constant, and now here you see J is independent of the pressure drop. So the pressure does not come into the picture in ultrafiltration, whereas in the microfiltration pressure plays a important role, it is almost like a normal filtration. You see the difference? Okay. Now there is going to be rate of loss of solute because solute will always try to escape. Now that will be equal to solute flowing through as permeate. Okay. So the rate of loss of solute will be d by dt V into C. V is your volume and C is your concentration, obvious, right. So we have a negative term because there is going to be decrease, anything decrease is that. Now this is equal to solute flow is J is your flux into area into Cp, that is concentration of the solute in the permeate. So this is also obvious, understand. So here you have rate of loss of solute is equal to solute flowing through the system as a permeate. Now this you write it as the Cp, you write as C into 1 minus R. C is the concentration of the solute in the retentate, that is the concentration that is remaining, and R is your retention coefficient. So if the retention coefficient is 0, okay, then C and Cp will be the same, whereas if the retention coefficient is 1, so this will get cancelled off. Okay. So rate of loss of solute on the left hand side, solute flowing through as permeate on the right hand side. If the retention coefficient for a solute R is equal to 1, then Vc will be a constant, understand. So if R is equal to 1, this whole term becomes 0, so dVc by dt equal to 0, so Vc is a constant, right. So a constant volume of solute will get lost over whatever time you are talking about, but R is generally 1, less than 1, okay. So when R is less than 1, now on the left hand side we can differentiate both this separately. So we will have minus C into dV by dt minus V dC by dt, which is equal to JC into 1 minus R. Now dV by dt will be J into A, that is the J is your flux, A is the area. So when flux by area is the your rate of flow of liquid, correct, that is why. So we can replace this by JA, and now V, the volume will slowly keep decreasing because of the concentration polarization, agreed. So Vi could be your initial volume minus J is your flux into area, that is rate, into time. So we are considering something like a linear decrease, okay. The assumption here is a linear decrease in the amount that is flowing through. So V by Vi minus J into T. Then we can integrate the whole system at T equal to 0, C is equal to Ci, that is initial. At T equal to T, C is equal to Cf, understand. So we can integrate this, all we do is replace this with this term and replace this with this term, and then you integrate. So finally you may end up like this: Cf concentration final, Ci concentration initial, Vi is your initial retentate volume, Vf is your volume, then you have the R coming there. So the amount of solute that is lost, Vi into Ci is initial minus Vf into Cf final. So this is the total amount of solute lost in that period of time, understood, in some T time. Now if you want further details, you may have to look into these particular references where they have given this derivation, and this particular slides are based on those derivation. So we looked at some of the governing equations in both ultrafiltration and microfiltration, and so we can use those equations to get a feel of what is happening to the process of membrane filtration. Now let us move forward. Now in ultrafiltration there is a term called nominal molecular weight cutoff, NMWCO, that means the molecular weight cutoff for which it is designed, okay. So if they give NMWCO as 20,000 Dalton, so it will cut off at that value of 20,000 Dalton, okay. So molecular weights bigger than that will be retained, molecular weight smaller than that will flow through. So if we have a NMWCO as 10,000, molecular weight greater than 10,000 will not pass through, molecular weight less than 10,000 will pass through. So when you are buying a membrane, ultrafiltration membrane, they give a term called NMWCO. So it represents the molecular weight for which a rejection coefficient is a fixed percentage, that means about 90%, because we cannot talk 100%, right, that is why we give it as 90%. So the molecular weight greater than that NMWCO will get retained or rejected. Retained means we talk about 90% of it getting rejected, okay. So retained or rejection are the same. So when this particular number is characteristic for a ultrafiltration membrane, okay. Now let us go to another membrane technology. This is a very important membrane process. It affects a large percentage of people who are suffering from either kidney damage or inefficient kidney system, where the urine does not separate out properly from the blood, that means the salts in the urine are not separating properly, or if it is a congenital disease, that means there are children who are born with this type of problem, then they have to resort to hemodialysis, and it is quite painful. They have to, it is not physically painful, but the patients have to undergo this type of treatment every 1 week or 2 weeks or and so on actually. That means the patient every week goes and spends about 2-3 hours and an artificial kidney is attached to him or her, and this particular instrument removes all the salts from the blood and makes it normal, and we do not realize our kidney does this job every day, day in and day out, and people who have this problem either should get a kidney transplant, and nowadays getting a kidney transplant is impossible because there is a large shortage of kidneys in India itself. There is a very large shortage, and so many of them will not be able to get kidneys, number one. Number two, sometimes the kidney can body can reject the kidney, you may have a kidney transplant, but the body can reject the kidney and then it becomes totally useless. So generally a kidney transplant within a relationship is always favorable because the rejection ratios are much low. Okay. So if somebody who cannot get a kidney transplant and who has a problem in getting the salts in the blood like uric acid and other salts, they may have to undergo this particular hemodialysis. So what is a hemodialysis? So there is a membrane, it is a long tube fibrous membrane, and then you have something called a dialysate, that is a fresh dialysate, it is nothing but salts and water, that is all. Okay. So it is flowing, and it is flowing because you apply some air pressure. Now the blood from the artery comes, that means from the patient, it goes through this particular fibrous membrane. So all the salts gets diffused and they go to the dialysate, and the blood that is leaving will be free from all these salts. So this is called the used dialysate, which will have all the salts, toxic salts present in the blood. So that is why this is called a artificial kidney. So it is a fibrous long tube. Here you introduce fresh dialysate, and here what you get is a used dialysate. Okay. So it needs to be processed so that it gets converted into fresh dialysate. So whatever toxic salts that are there which it has taken from the blood will be removed, and then again it is put back. So this is it looks very simple, but it saves thousands and thousands of patients who have problem with the kidney. Let us look at what it does. So it is hemodialysis is a dialysis unit in the medical field. So we can use it even in your manufacturing process where you are interested in separating out certain salts from certain solutions. It can even be used for separation of alcohol from beer and so on. So what is it doing? The blood is drawn from the patient, passed through the lumen of a hollow fiber unit. Okay, there is a long hollow fiber, water containing solutes, that is called the dialysate, such as potassium salts, pass through the outer side, that is the shell side. Why do you add salts to the water? So that it will also have same osmotic pressure as the blood. Otherwise what will happen? If there is an osmotic pressure, water will start flowing into the blood. You do not want that to happen, understand. That is why you do not just pass water in the outer side of the fibrous membrane, you also have salts so that the osmotic pressure is balanced and there is no water ingress into the blood. Okay. So what happens when these two liquids flow? Urea, uric acid, creatine, phosphates, chlorides diffuse from the blood into water and your blood gets purified. It looks quite simple, but it does a fantastic job. So you can, the separation of solutes generally happen because of diffusion across the membrane from one liquid phase to another. So it is based on the concentration difference. So the blood has a very high concentration of all these salts and your dialysate has a very low concentration of this. So the driving force is your concentration difference. So the dialysis membrane, it does not have porous, it does not have non-porous characteristics like RO or microporous characteristic of UF. Okay. So it is in between both. It is not completely non-porous like reverse osmosis, or it is not it's got so many pores like ultrafiltration. So it is in between. So the process is very slow. Normally the patients who go for this type of dialysis treatment have to spend 4 to 6 hours. So it is a very long process. So if somebody has to do dialysis every month, imagine the person has to spend more than half a day lying down, a dialysis machine connected to the person. So if it can be speeded up, then people will be very happy actually. So there is a lot of research opportunities in trying to speed up this dialysis process also. So how can one speed up? one way is to increase the surface area, but you cannot increase the contact area too much because the flow gets disturbed. Okay. So what happens, there is a solute flux J which is equal to R is your resistance, delta C is your driving force, obvious, right. Now the resistance are manifold, resistance because of the membrane itself, resistance because of the film on the blood side, resistance because of the dialysate salts on the other side, agreed. So there are 3 resistances you need to consider. R is made up of 3 resistance. So the blood is flowing, dialysate is also flowing, although I have shown it as counter current, generally co-current is preferred. So if you have the dialysis membrane, there is going to be a film in the blood side and there is going to be another film in the dialysate side. So the salts have to diffuse through these 3 films, the film which is formed by the salts in the blood side and the film that is formed on the dialysate side, and in between you also have the membrane material. Okay. So the equation for the flux is given by this resistance multiplied by delta C, delta C is your driving force, concentration gradient. Okay. Now there is something called dialyser clearance, that means it tells you how much the rate of removal of a substance from the blood. Okay. When you say rate of removal, we will say there is always a time per minute or per second per hour. So it depends on many factors, characteristics of the dialyzer, nature of the treatment and so on. So if you look at the mass balance for your particular solutes C, you have Kd, okay, that is your clearance, Ci, okay, that is the amount of solute that is removed, that is equal to Qi into Ci. Qi is the input blood flow, that is at the inlet, Q naught is the outlet blood flow from the dialyzer, agreed, obvious. Ci is your concentration of the solute in, C naught is the concentration out, obvious. So you have concentration of solutes coming in into Q, and again you have concentration of solute leaving into Q, this is equal to amount removed Kd into Ci. Okay. Generally C naught will be much smaller than Ci, because in your dialyzer the main goal is to remove the salts. So obviously Q naught has to be very small, no problem, right. So we can combine these equation. If Qf is the ultrafiltration rate, that is some blood flow also happens, that means blood escapes through the membrane and reaches your dialysate, then Qi, that is the amount of blood coming in, will be equal to Q naught plus Qf. You do not want blood escaping into the dialysate, right, but it can happen in some situations, so do not forget that it can happen. In generally we can assume some number, so we can substitute all these and we get an equation for Kd, that is the clearance. What is Kd? Dialyser clearance, removal rate of a substance from blood, that is given by Qi, that is the blood flow into the dialyzer, okay. Q naught is the blood flow out leaving, Qf is the blood escaping through the dialyzer, C naught is the concentration of the salts entering your dialyzer, okay. Ci is a concentration entering, C naught is what is going out. Generally Qf is equal to 0, generally blood will not escape, and then generally all these quantities are same, that means Qf will be equal to Qf and so on actually, right. So a very simple equation comes out, the clearance Kd is given by Qb, that is the amount of blood, rate of blood flowing through the dialyzer, 1 minus C naught by Ci. Ci is the inlet concentration of the solute, C naught is the concentration of the solute leaving the dialyzer, and generally C naught is greater than Ci or less than Ci. C naught will be less than Ci, very small, because we are trying to remove the salts, right. So, C naught will be less than Ci, agreed. So, this gives you an idea about the clearance. Okay. Now, solvent flow across the membrane also occurs in dialysis because of osmotic pressure difference. Okay. So, there is some osmotic pressure. So, there is some loss of water, and water may enter into your blood and so on. Okay. And generally we use a co-current type of flow to avoid a pressure drop across the membrane. So, these are some points which one needs to think about in the case of a dialysis. Now, let us go to something called electrodialysis. Electrodialysis, as the name implies, electro, we apply a very large potential difference. So, when you apply a large potential difference, cations will go to where? Cathode, anions go to the anode, okay, and they get separated out because of the large electric force. And we have cation favoring membranes, anion favoring membranes, or selective cation selective membranes, anion selective membranes. So, in an electrodialysis you have many chambers or many compartments, and each chamber is separated by one set of membranes, okay. They are called ion selective membranes. So, you may have cation selective membranes, then you may have anion selective membranes, you have again cation selective and so on actually. And then you are applying a very large voltage, you see anode, you see cathode here. Now, imagine I have a protein and a salt solution. When do you have a protein and a salt solution? Especially if you are doing salting out. When you do salt out, you add lot of ammonium sulphate. So, your protein solution will also have salt solution. So, first step is to remove all the salt. So, electrodialysis is very good because salt is ammonium sulphate, it will nicely ionize, and I can put a large voltage and I will be able to separate them out, that is the whole idea. So, that protein can be recovered in water. Now, suppose I have a protein in salt solution and then I am passing water. So, water is passed into alternate chambers, protein is passed into alternate chambers. Now, you are applying a very large voltage, and then you have anion selective membranes, cation selective membranes alternatively. What will happen? Look here, now your salt gets ionized, agreed. So, the pluses want to go there. So, if it is a cation selective membrane, it will nicely go there. Now, imagine a minus will not be able to go there, okay. So, minus has to, which wants to go to the anode, and this is an anion selective membrane. So, the minus will go here, okay. Now, this plus wants to go there, but it cannot go because there is a anion selective membrane. So, it will stick here. So, what will happen? You have alternate chambers with plus and minus, and the alternate chambers will be pure, free from salt. So, you will have alternate chambers without any salt and alternate chambers with high concentration of salt. So, what will happen? You will have protein in water in alternate chambers, it will be free of salt, and you will have high concentration of salts in the alternate chamber, understood, okay. So, I can nicely recover my protein from the alternate chamber which is in water medium, and all the salts would have gone to the alternate chambers. This is the how system by which electrodialysis does its job, very interesting. They have got lot of advantages, disadvantages. It is very good for doing this, but there is heat generation because you are applying high voltage, energy consumption is very high, membrane material you need to replace from time to time because of fouling and so on actually. There are different types of fouling happening here, erosion of the membrane surface, all these happens actually. But it is a good system to have because you will have alternate chambers without any salt, that means pure water, and alternate chambers you will have very highly concentrated salt present actually. So, that is the advantage of this type of electrodialysis, Okay. Now we can use it for desalination of brackish water. So what you can do is we can use electrodialysis, all the slurry of salts will be in the alternate chambers and remaining alternate chambers will be free of the salt, and so we will get drinking water. Separation of ions occur due to the potential difference across the and selective cationic and anionic ion exchange membranes, as I mentioned actually. So it will have a stack of compartments, sometimes you will have 20-30 stacks actually, and each stack will have alternating membranes like cationic, anionic and so on actually. So the driving force here is what? There is an applied electric field. Now this induces a current and there is a flux across the compartments. This is what happens in an electrodialysis. So positively charged species goes through the cationic membrane, negatively charged species go through the anionic membrane, and because these membranes are very selective, so this other type of charged material will not go to the non-selective membrane. So we can use it for selective separation of mixtures of ionic species, depends on the difference in ionic mobilities also. So some smaller ions may be able to go diffuse much faster, so they are much more mobile. Larger ions will take much longer time, so we can use it as a function of mobility as well. So the effluents, that means the liquid that is coming out of alternate compartments will be concentrated of the ionic species and depleted of ion species. So you will have concentrated, depleted and so on actually. So that is the advantage of this particular setup. So there is a mathematical relation which connects the current that is flowing with the charge particle details, you know. So you have current I is equal to, this is a constant, it is called Faraday's constant, N is the solution normality, Q is your flow rate, eta is your efficiency, N is your number of cells, E is your current efficiency. So eta is a removal efficiency, E is your current efficiency, do not forget. Now F is the Faraday constant, so this is the normal number for the Faraday constant, okay. Now using this equation I can calculate, if I know the flow rate, if I know efficiency factors little bit here, if like this efficiency and this efficiency, okay, and N gives you number of cells. So if I know all these, I may be able to calculate what will be I, that means what will be the current. Now there is another term which is very important, that is called the electrodialysis power, that means how much power should I put in for this particular operation. So if I calculate my current from this equation, I can substitute here, and if I know the resistance of the entire setup of N cells, that means N compartments, when I say cells it is N compartments, I will be able to calculate the power. So it will give me an idea of the power requirements for performing an electrodialysis type of operation. There is another equation which also gives you a flavor of the process that is taking place, that is called the Stephen-Maxwell theory. So that gives you a force on each charged component when it is present in an n component mixture, okay. So we have it is a summation, because when you have n component mixture each component will undergo or experience a force because of another component, that is why you have summation here, we have Ci, Cj, okay. Cj will be running from 1 to n, small n, where small n is the number of components, okay. Dij is the Stephen-Maxwell diffusivity, okay. So left hand side is all the driving forces exerted on a species, okay. Right hand side is related to all the friction forces actually, okay. Now you have the concentration, Ct is your total concentration, P is the pressure, R is your universal gas constant, T is your time and so on actually, okay. So this tells you what is the force that a particle of certain charge experiences in the presence of many particles, that is n particles. We will not go too much into that, that is too much of a fundamental study, whereas this equation may be much more useful, which gives you an idea about the amount of current when you have n compartments, when you know the efficiency of the removal process, when you know the efficiency of the current, when you know the solution normality, and when you know the flow rate. Okay, this equation is much more useful, and of course this gives you an idea about the power. So this equation is also pretty useful. Now based on this equation, let us look at a problem. So I have an electrodialysis unit. This is used to remove 2.2 moles of ammonium sulphate from a dilute solution of protein. So you are passing a current of 176 ampere. How fast should the feed be introduced into the compartment to remove 99.9% of the salt? Okay. So I want to remove 99.9% of the salt. I want to know Q, and the amount of salt solution that is flowing in contains 2.2 molar ammonium sulphate, and I am passing 176 amps. Okay. So how do you solve this? So we know 1 amp is equal to 1 coulomb, and 96,487 coulombs is 1 mole of electron. Okay. If I take 1 mole of ammonium sulphate, there will be 2 moles of electrons, right, 2 SO4 double minus. So you will have 2 electrons. So all you need to do is substitute them into this, and then you will be able to get the value for Q. Now Q is Q into 0.99 is the amount of salt that are removing. Okay. So from there we will be able to calculate Q, understand. So the problem is I have so many molars of salt solution flowing at a particular rate, and I want to remove so much of the salt from a solution. I am passing so much current. So what should be my flow of the solution? Okay. So this comes from the ionization of the salt. In this particular case ammonium sulphate NH4 2SO4, so there will be 2 electron flowing into that, whereas if it is sodium chloride it will be 1 electron flowing into that. Okay. So do not forget that. So that is how you calculate the whole problem. Now let us go to again a process which makes use of a voltage, that is the electrophoresis. We all have come across this in analytical lab, where you want to separate proteins of different charges. Okay. So all proteins have some charge. Why? There are nitrogens and COOH. What COOH? That is the acidic group. So there is going to be COO minus, that is a charge. Sometimes nitrogen will have N plus, so that is a charge. So proteins will always have charges, do not forget that. Okay. So there is one pH at which proteins will have net 0 charge, and that is called the isoelectric point. Okay. So if we are operating away from isoelectric point, proteins will have charge. So if I apply a voltage, okay, proteins will start moving. So if I have proteins of different molecular weight or different sizes, and they are all plus, I am applying a large voltage, they will all get attracted to the negative minus, correct, cathode. Now the speed at which they get attracted will depend upon the mobility, that means it will depend upon the size. So I can achieve a separation based on the size. Okay, this is how electrophoresis work. You agree? Now if you neglect gravitational forces, the force on the charged protein will depend on the electrical potential, that means how much potential I am applying, and the mobility divided by delta x. Delta x is the distance between the 2 electrodes. So if the delta x is very very large, the mobility, the rate, the speed at which the protein or the velocity at which the protein is moving will get decreased. If my electrical potential is large, the speed at which the protein is moving will be high. and if the mobility is very large, then the speed at which the protein is moving also will be very high. Now this mobility is again dependent on several factors: d, the diffusion coefficient; z, charge on the protein; f is your Faraday constant; r, T, universal constant; and T is thermal. So you see here the mobility you can see is a function of diffusion coefficient, mobility is a function of a charge. So if I have very large charged protein, it will move very fast towards the cathode. If the charge is very low, it will move slowly. So if I have a protein with charge 2 minus plus 2, and if I have protein with plus 1 charge, the plus 2 charged protein will move faster, right, than the plus 1 charged protein, okay. And but of course you have something called diffusion coefficient. If the diffusion coefficients are different between the proteins, then that will also affect their mobility. So not only the charge on the protein that is an important, but also the diffusion coefficient. So sometimes if you have a very large protein, the diffusion coefficient may be very poor, then the movement will be retarded, that means it will be moving much slowly. Whereas if you have a protein which is much smaller, then it will be moving much faster, that means the diffusion coefficient will be much larger, then the mobility also will be larger. So the size of the protein matters, the charge on the protein matters, so both matters actually, understand. So you look at mobility, you have for albumin 5.9, gamma globin 1, that means it is almost 6 times slower, fibrinogen minus 2.1, that means albumin is 3 times or 2 times faster than fibrinogen, and fibrinogen is about 2 times faster than globin, okay. So you see large difference in the protein mobility. Okay, let us look at a small problem using this approach. I have 2 enzymes A and B to be separated by a gel, electrophoresis. Generally we use this particular approach, electrophoresis, for separating protein. I am doing it at 4 degrees centigrade. Now the diffusion coefficient of protein or enzyme A is this much, the diffusion coefficient of enzyme B is this much, that means this has got a higher diffusion coefficient than this. Now this has got higher charge, see, this has got 7, this has got only 1, okay. So because of charge this protein may move faster, but because of diffusion coefficient this protein will move faster. So this is the equation, the velocity, diffusion coefficient, the charge, Faraday constant divided by R into T. Now we are applying a field of 1.8 volt per centimeter. How long it will take to separate them by a distance of 2 centimeter? So how long it will take so that they are 2 centimeters away? So now I can calculate velocity A, I know dA, I know ZA charge, I know Faraday constant, I know RT. So I can get VA, agreed. So for VB you have dB, ZB, FRT, so I get VB. Now this protein is going at a velocity of 6.1 into 10 power 5 minus 5 centimeter per second, this protein is going at 2.4 10 power minus 5 per second. So velocity A minus velocity B into time will be equal to distance, correct? Velocity into time is distance, agreed. So VA minus VB into time will give me distance, distance is 2 centimeter, I want to push them 2 centimeter apart. Now VA is this much, VB is this much, so time comes out to be 15 hours. So I run this electrophoresis for 15 hours so that the 2 proteins get separated by 2 centimeter based on the protein charge, based on the diffusion coefficient of the protein, correct. Now this is how you use to calculate how long should I apply this particular electric field so that the proteins get separated by say 1 centimeter or 2 centimeter or 3 centimeter and so on actually, okay. So this problem, very simple problem, tells you in the electrophoresis system how do you separate out proteins, okay. Now the simple equation, so you have velocity, we have the mobility, we have the the electric potential or the force we apply divided by the delta x. Such a simple equation we make use of and calculate what should be the time required to separate these two proteins by 2 centimeter apart. Okay. Now let us look at another membrane separation process, that is called pervaporation. It is a combination of permeation and evaporation. So we can separate 2 or more components with the help of a very thin pervaporation membrane. So if one component has certain rate of diffusion, another component has another rate of diffusion, these two can be separated. Pervaporation is not based on filtration because there are no holes in the membrane. The solute gets sort of dissolved inside the membrane, it gets diffused and it comes on the other side. So you have a vapor on one side. How do you achieve vaporization? You heat it up, okay. So there is going to be a vapor on one side, then that solute gets dissolved in the membrane, it travels through the membrane and then on the other side it is collected and it becomes a liquid. So what is the driving force? You apply a vacuum on the other side. So you have a heating on one side and you have a vacuum on the other side, and the membrane does not have any pores or holes. This is what pervaporation is. It is a combination of permeation and evaporation. Okay, how does the setup look like? Simple one, very simple. You have a pervaporation membrane, you have your feed, you heat up the feed so that it gets vaporized, so it comes here and you are applying a vacuum on the other side, so that is the driving force. So the vapor gets dissolved in the membrane material, it travels or diffuses through and the vapor comes out on the other side, it is condensed in a condenser and you collect the liquid. So here you are applying a heating so that the feed gets vaporized, here you are condensing the vapor and the driving force is your vacuum here, and there are no pores in the membrane. So the process is permeation and evaporation. So permeation is like a diffusion, not like a filtration here. So you have hydrophilic membranes, hydrophobic membranes, that is membranes which favor a particular type of material. If you want to recover only hydrophilic solutes, then you go for hydrophilic membranes. If you want to recover hydrophobic materials, then you have a hydrophobic membrane. So if you have a hydrophilic membranes here, hydrophilic material will permeate through or diffuse through. If you have a hydrophobic membrane, you will have a hydrophobic material will permeate or diffuse through. So that is the difference. So this process is very good, it is being used quite a lot for concentrating fruit juices or dairy products. It can be used for separating water from alcohol, so we can get 100% alcohol here. So the membrane will pass only water through, and as you know we cannot get 100% water by distillation because water forms a azeotrope and distillation is not possible. So in such situations we use pervaporation. If you have fruit juices and I want to remove some water, I can't heat it up because fruit juice will get totally charred or burnt. So here you will have a hydrophilic membrane and only water will go away. So this side you will get more concentrated fruit juice. So this process is already being commercially practiced in many places, especially for food as well as for concentrating as well as for water removal as so on actually. So we shall continue more on this pervaporation process in the next class.